Hello, this is going to be a Matt workshop for the Oxford Maths Online Open Days. Welcome back, nice to see you again. I'm saying welcome back in case you were here earlier for the welcome session at the start of the day. This is going to be some math questions. I'm just going to give people a minute to filter through to join us from the Open Day page. I hope you're enjoying the Open Day so far. Making the most of bits and pieces that we pre-recorded or other resources. If anybody's got the Google Earth thing to work in 3D, I'd love to know. So the way I'm going to run this is I'm going to show you some math questions and a warm-up question, and we're going to use the Q&A chat thing to, it says Q&A, we're going to use it like a chat feature. So you can put things in there if you want to answer the questions or just suggest things or ask questions about maths, but things don't need to have a question mark on, just put whatever over there. Okay, I should say now, in case anybody's watching this, if you've joined us and you don't know where you've come from, this is going to be the same math workshop that I did earlier today, and it's the same math workshop that I did twice a week ago. So if you joined us earlier today, or if you joined us last week, or if you've watched one of those videos already, then you've already seen this math workshop. I'm doing it live at lots of different times for people's convenience of joining in live. There's now quite a bank of resource of pre-recorded videos. Watch the live stream back of me doing this workshop multiple times. But if you've already seen this, then you don't need to watch it again. You might be interested in the math live stream, which is going to start on the 5th of August. Right, I learnt earlier today, sorry people who've joined us from the Open Day live, I learnt earlier today that people are watching all of them getting disappointed that they're all the same. We're doing this at the convenient time, and you've sort of won the game theory thing of choosing which session is going to be more or less popular, because I think you want to be at a session with fewer people, because then it's more, you get more attention paid to you and what you're saying, being in a smaller session, yeah, you've won that game theory thing. The other session had more people at it so far. Well, some more people just joined actually, so we'll wait and see. Okay, right. It's a bit of rambling while people join us. Hello, nice to see you. I'm going to put a thing on the board. Here's a sort of warm-up exercise. Get used to working with exponentials and logarithms. It's a Saturday afternoon. Got to get maths warmed up. Here's what I'd like. I've got 2 to the x to the 3. I would like to know what's that equal to. Can you tell me anything else that's equal to? Matt Parker in chat live, possibly Matt Parker, says, thanks for running this multiple times. If you apply to Warwick, Oxford Imperial, do you take the math multiple times, or you take the math once? You take one math paper, and it gets used for all those applications. So Matt's come to a couple of these. And, yeah, luckily, Matt, you only have to do the workshop once, and you only have to do the exam once. So someone anonymous in chat has put nice and quickly that this is equal to 2 to the 3x. That's true. Is this equal to anything else? Matt's in. Matt's in. Thank you. And 8 to the x, says Matt. Were you here earlier, Matt, or do I just recognise your name because you're using the name of Matt Parker? Maybe you weren't here earlier, I forget. Were you here for the Q&A, maybe? Yeah, we had a question from Matt Parker earlier. Okay. So if you do the workshop multiple times, then you can learn the answers quite quickly. See if Matt Parker can be one question ahead of me for the rest of this. Just like real life, Matt Parker's always one step ahead. Okay. Someone in chat says they've been to all 4, so you're going to get really good at what's coming next. Anyway, no, I'm going to focus on people who haven't been to all 4 workshops. So can I write this as anything else? This works, I suppose, because 8 is 2 to the 3, and 2 to the 3 to the x is the same as 2 to the x to the 3. Brilliant. Can I write this as anything else? So last weekend I had a problem of people came to the first one and then they came to the second one and just said all the answers straight away, but with the same usernames, so that I knew what they were doing. Anyway, I'm running it twice. I thought it was the right thing to do, to run it multiple times. Maybe 4 times was too many times. Anything else we could write this as? For example, could I write this as 4 to the something? juggling around with powers like this is, I suppose, good practice of exponentials. And also good because you're sort of playing with the idea of what different bases could be. I want you to get away from everything being stuck on one base. Tom says 2 to the x times 2 to the x times 2 to the x. Like it. Anonymous, best username. Root 8 to the root 8 to the 2x. Oh, I've got to think about that one. Root 8 to the 2x, bringing in some radicals in here. Lovely stuff. Can we write it as the cube root of something? Probably. Log base 8. Oh, right, okay. There's some logarithms from Kieran. Who's brought in a y as well. I guess if this is y equals something, then Kieran says that log base 8 y is equal to x. That looks true. I agree with that. Yeah, logarithms. Yeah, 4 to the Cecily and Matt Parker as well, I think, actually. We've got 4 to, I think it's 3 over 2. I think it's not quite 2x. There's a separate question. Is it something to the 2x? I think it's this. Because I could take this 2 and I could write it as 4 to the half. 4 to the half to the 3x is 4 to the 3x over 2. Brilliant. Messing things around. Cecily, you've put a question mark on, and I need to. It's fine. You don't have to put the question mark on. I know that it says Q&A and it says ask us anything, but Slido's not actually checking if it's a question mark. So if you've got some true mathematics, you don't need to put the question mark. Yes, 4 to the 3 over 2x. There's a little bit of stream lag. The stream lag is, I think, different for different people watching in different places. So I say something and different people hear it at different times. So you get different bits of lag in chat. Yeah, 4 to the 3 over... Oh yeah, okay, we could write this as 4 to the 3 over 2x, like this. Not quite sure if people are answering the same thing. Oh, okay, e to the log 2... Yeah, and Matt would like something with an x with an e in it. I've got to think a little bit. I'm continuing a pattern though, so I've written it as 2 to the something, 8 to the something, 4 to the something. How far can I push this? Can I write this as 3 to the something? Is that allowed? Can I do that? Matt would like e to the... Oh, I've got to copy this down. E to the ln 2, and then there's a power. Where do I want that power? Yeah, I'm going to put 3x like this. I think this is what you want. I think you want extra bracket. I think you want your bracket slightly different, but I agree with your second thing. E to the log 2 3x, because then that's like writing this this 2 as e to the ln 2. Yeah. Yeah, I think you want times, not 3. Okay, cool. 16 to the 3/4. That sounds good. 16 to the 3/4 x. Yeah, sounds about right to me. Yeah, because 16 to the 1/4 is 2. So yeah, this is all equal. Can I do it? No one's given me 3 to the something yet. So that's a little bit weird. Excuse me. Good. Tom's had a go. Oh no, here we go. We've got people giving me things with logarithms in. Got to be careful with the bases of the logarithms. Yeah, 3x log 2. That's this thing, isn't it? That's this thing that we were working on. 3 to the... Ooh. Tom's got a thumbs up from someone of 3x ln 2 over ln 3, and someone else has given that a thumbs up in chat, so I'm going to assume that's right. I suppose the maths that we're doing here is something like... let's put a box. The maths we're doing is something like 2 to the 3x equals 3 to the something, so I want something like log base 3 of 2 to the 3x is equal to that. Do logarithm base 3 on both sides. If you've seen logarithms, then you can play along with this sort of game. Use, yeah, I could even write this as ln, if I wanted to, ln of 2 to the 3x over ln 3. I think that's what's gone on here. Yeah, this looks similar. And then laws of logarithms. Yeah, the symbols are impossible, aren't they? We've gone into the space. Somebody says I can't write proper symbols on a laptop. Yeah, goodness knows. people have worked out that we're using this symbol for powers of, but then it's not really clear how you write logarithms and stuff. Yeah, 27 to the x log 3. Yeah, that looks nice. Something like that. Yeah, okay. Yeah, you can change the base and the exponent as you like, as you see fit to pair things together. It's this 3 thing that I want to zoom in on, because it sort of feels weird to write something that's a power of 2 as a power of 3. You can't really do that for whole numbers, right? That if the powers are whole numbers, then you can't have a power of 2 being equal to a power of 3. Let me write this down. So let's say you let's start again. Not if. Be bold. Let's say you can't have 2 to the p equals 3 to the q for positive numbers. Positive whole numbers, integers if you will, p and q. Can't have that, because if you do this, then you'd have, you could take the logarithm of each side. Yeah, so someone in chat says some people might not have the link to join this section. I can't really help them if they don't have the link. But you're right, that if people are in the Q&A and they're wondering what's going on, if people are in the Q&A and wondering what's going on, then I guess I've seen loads of people talking about logarithms suddenly, out of nowhere. But I've put a link in as well. Okay, we'd have this, so then we'd have p over q is ln 3 over ln 2. Think of those as some numbers that I've seen in chat. And because you can't have this for positive whole numbers p and q, you can't have this because this one's even and this one's odd if these are positive whole numbers p and q. So ln 3 over ln 2 must be irrational. This is a proof that log 3 over log 2, basically, or base whatever, log 3 over log 2 is irrational, because if it was equal to p over q, then I could multiply up, take exponentials of each side, and haha, I've got 2 to the p equals 3 to the q, but can't have that for any positive whole numbers p and q. Of course I can't. 2 to the p is even, 3 to the q is odd. So this is a proof that this number is irrational, can't be written as p over q for whole numbers p and q. And I like it because it's easy. The proof that you might have seen before, that the square root of 2 is irrational, has lots of steps to it, and it ends up arguing about whether there's a common factor or not in p and q. So you have to say, suppose the fraction is written in lowest common terms, and then do this maths involving the square root of 2, and now you've found a way to write it in lower terms so it doesn't work. And that's quite fiddly. Whereas this proof, that log 3 over log 2 is irrational, is really easy. It's just, well, take log 3 over log 2, write it as p over q, if you could, multiply up, do some exponentials, hey, I've got 2 to the p equals 3 to the q, can't do that, so that's irrational. Someone showed me this once and told me that it was, in their opinion, the easiest number to prove to be irrational. Out of all the irrational numbers, and there are lots, some are very hard to prove to be irrational, some are very easy to prove to be irrational. Maybe this is the easiest one to prove it's irrational, so maybe we should do that one instead of square root of 2. Right, okay. I feel like everyone's seen square root of 2, nobody's seen this one. Right, okay. What are we doing? We're going to do some math now. The way this is going to work is I'm going to put a math question on the board. Math question. It'll look horrible because it's a math question. Math questions are supposed to be difficult. They're supposed to be the sort of questions where you look at it and it's not obvious what you're going to do. So usually at the start there's this part where you stare at the math questions, like not clear at all how you're going to make progress. You've got to explore things, try out different ways of attacking the problem to start off with. It's not obvious that any of them are going to work, and then try and find a way through. Right, I'm rambling to give you a chance to have a go at this question, and I've also got a poll in the Slido. Let me switch this on. This, good, cool. Okay, so if you can do this question, then you can vote. Or if you want to say a way to make progress with this question, then you can use the Q&A. In Slido now, I think there's like tabs, so you can click on the Q&A if you want to. Click on Q&A if you want to say something about how to make progress, or click on the poll if you want to vote for an option. And then at the end we'll see what people have got. Okay, I'm sort of rambling to give you a chance to try the question while I chat away. I could just shut up and let you do the maths, but it kind of feels like I don't want to leave dead air of nothing happening. People have got some pretty good suggestions in chat. In fact, it's got to the point where I'll say, if you don't want a hint, don't look at chat. Don't look at the Q&A box. If you'd like a hand, if you'd like a clue, then have a look over at the Q&A box. But people's comments are very good. So if you haven't found a way to make progress already, it's not been long, then keep trying at it. I'm going to read out the question and try and explain some ways I attacked it. So the equation 9 to the x minus 3 to the x plus 1 is equal to k. We're asked to complete the following sentence. This is a style of math question where there's kind of a sentence that we have to select the right answer to the sentence. Don't ask me why they've got commas. Anyway, so the equation has one or more real solutions precisely when, and then there are 4 options of how to finish that sentence, different ranges of k. Okay, so the equation's horrible. It's got different powers with different things upstairs, different things downstairs. It's got subtraction, it's got 2 variables, it's got k and x in there. People are suggesting great stuff in chat. First thing that I sort of tried was maybe, rearrange it a little bit and try taking logarithms to try and get rid of the powers. That's quite tricky because you've got 3 things. If I just had 2, then I could split them apart, take the logarithms, and then work on the logarithmed versions. Because I've got 3, it's kind of whenever I do a logarithm, on one side I've got 2 objects, or 3. I've got 2 or more objects when I take the logarithm of that side. And log a plus b is really awkward. There's sort of working with log a plus b is just not fun. There isn't really a good rule for this. So I can't really make progress. And that's quite normal to sort of try something, not really know if it's going anywhere, not really know where it's going, and then find out that, aha, this hasn't worked, I need to try something different. If you do try something good along the way, then it's not always obvious that what you're doing is a good idea. Okay, people in chat are telling me, so I'm going to sort of start with the most, without giving the game away, things that people have said in chat. So someone in the chat has spotted that 3 to the x plus 1 is 3 times 3 to the x, which is nice. Cecily has also split this 9 to the x in terms of 3 to the 2x, which is pretty good. So maybe writing these things with a common base. So if we write this as 3 to the 2x minus 3 times 3 to the x is equal to k. Now, maybe at this stage I don't know where this is going, but it feels nicer to have 3's downstairs, right? So then perhaps I could write this one as, this is like 3 to the x squared minus 3 to the 3x is equal to k. To try and get things in terms of 3 to the x. And now this is looking like a quadratic. People are calling this the hidden quadratic and suggesting that we might do this quite a bit. It's a nice style of question, right? That you can solve quadratics and you can do substitutions. So pairing those things together can give you a kind of nice question with that effect of not obvious where you start, and then you do some rearrangements, and then quadratic or polynomial or something. Okay, yes, Rose would like us to use the discriminant next. So we've got down to a quadratic, and at this stage we're happy / excited / relaxed because we know loads of stuff for doing things to quadratic equations. People would like me to call that u, I think. Alright, u equals 3 to the x. Okay, suggestions for what to do next. Rose would like to use the determinant. Oh, discriminant, excuse me. You said the right word, I read it wrong. Discriminant for a quadratic. The discriminant for a quadratic tells you whether the thing's got one or more real solutions, right? Here the discriminant is something like, I need to move this k over onto the left hand side. And then I can do something like b squared minus 4ac. I want that to be bigger than or equal to 0 for more than one solution. So I get something like k, I want to be bigger than minus 9 over 4 or something, rearranging. one or more solutions, yeah, one or more solutions bigger than or equal to 0. Okay, that gives you one or more solutions for this. Yeah, cheeky hidden quadratic, I love it. Okay, looks like it's going to be option A, right? Looks like option A. And that is in fact what everyone's put in the poll, voting for people who got there faster than me, all got option A. K is bigger than -9/4. Sorry, my voice is going slightly after multiple live streams. Okay, we can do this. There's a small problem. And it ends up not mattering for this question, but I'm going to describe it anyway. Here's the problem. So technically, what we've done here, by checking for 2 or more solutions, this is one or more solutions. This is one or more real solutions for U, right? Because the quadratic's in U. And there's this tiny problem that maybe there's a problem that a real solution for U, does that always mean we get a real solution for X? So remember, U is equal to 3X. So this is like checking your solutions, right? So after you found some solutions, you go back and check them. So if we get one or more real solutions for U, it would be a problem if they didn't give us actual real solutions for X. In particular here, it would be a problem if both of these solutions, or these one or more solutions for U, if they're all negative numbers, then that's a bit of a problem, because our quadratic would be happily saying, yeah, I'm a quadratic, I've got one or more real solutions, of course I do. They're negative, but that's fine, that's real solutions, yeah. One or more real solutions with the discriminant method. But over here, when we try and work out X, oh no, 3 to the X, for X to be real, 3 to the X is going to be positive. So if U is negative, then this is pretty bad, because this will not give us real solutions for X. Doesn't matter for this one at all, because it turns out that there's always a positive solution for this whenever there's one or more solutions. Let me draw a little graph. So if I write this as if I draw a graph of U squared minus 3U, and we think about values of K, so that I don't have to sketch different values for different K, then U squared minus 3U would look something like this. That's U squared minus 3U. And at different values of K, you get these solutions. So you see here, when K is up here, I've got 2 solutions for U, so 2 different real solutions for U, but one of them doesn't correspond to a real solution for X. Because, I guess, to work out X, I would have to do a logarithm. If I was working backwards to find my solutions, I'd have to do a logarithm. Here, I can't do a logarithm of a negative number, so actually only this one would give me a real solution. So, in a way, this one is a kind of problem. This bit's problematic, because these are real solutions for U that don't correspond to real solutions for X. So that's a little bit problematic, but it's okay. This bit sort of saves the day, and solutions over here are good because that's a solution for U and it's positive, so it also works out to be a solution for X. Okay, and it exists all the way from here upwards, so we're good. Okay, so we can do this too. So in fact, the answer really is A. So long as K is bigger than -9/4, which is the value down here, as long as K is bigger than -9/4, there's at least one positive solution. And because there's a positive solution, we can work out X from there. So this question could be slightly harder. I'm just saying this so that you're aware of it. Not really for Matt, I suppose, although a Matt question could do this. If we set the same Matt question again with a small tweak, if we set this but said, when does this equation have 2 or more real solutions, then there's a kind of trick, because the quadratic has 2 or more real solutions, as long as K is bigger than -9/4. Of course, it has 2 solutions, here's one, here's another one, here and here. But there's only 2 real solutions for X if both of those roots are positive. Because I want to put positive numbers into my logarithm, so I'd need to stop here. When this root goes through 0. Okay, so I'm going to make this question harder by putting in 2 or more. Alternatively, kind of exercise to try at home, if none of that made sense, then exercise to try at home is to think about 9 to the x plus 3 to the x plus 1 equals k. So same question, different answers, but same question. If it's 9 to the x plus 3 to the x plus 1 equals k, when does that have one or more real solutions? And there you've got to be careful. The discriminant is the same, but the discriminant is the same, but the answer's different. Okay, 2 questions in chat. Will there be a maths problem with the Riemann zeta function? We would not assume any knowledge of the Riemann zeta function for a maths question. There's a very limited syllabus of maths that we expect you to know. It's one page of A4 with topics on of basically just the first half of single mathematics A level, few topics from the second half of maths A level, no further maths, no Riemann zeta function on there. That's the maths that we assume you know, and it's stuff that we expect you to be good at, like solving quadratics or like using the discriminant for quadratics. It doesn't include very advanced maths at all on there. It's stuff that we expect you to be good at, so that if a question turns into, you've done some work and you've shown that the question turns into this, then after there you can relax and do some quadratic stuff. Can we set a problem involving the Riemann zeta function? I suppose we can do a style of question where at the start of the question we introduce something, we explain, like here's a new idea. We might say, you've heard of quadratics. A function is sporadic if it does, and then tell you that a function is sporadic if its derivative is 1 minus itself or something mad, and then give you something to work with where we're not really assuming knowledge, we're showing you some new mathematics and then getting you to work with it through some parts of the question. We could do something like that. Could I do that with the Riemann zeta function? Probably not, because Riemann zeta function sounds really hard. Yeah, Matt is trying to do my extra question. Matt Parker says it's reflected, so something like bigger than 0. I think it's not quite B. I think you want B bigger than or equal to 0. Which reminds me, someone said earlier, well, so I've skipped a comment that's, how did you solve that inequality so fast? Partly, I solved that inequality quickly because it's just minus signs and I'm good at multiplying minus signs. Partly, because this is the 4th time I've done this workshop, I know which is the right answer, so I can skip steps. Don't copy me. Someone earlier said you could try values. Where did I see that? I want to find out who said it. Tom in chat said, try solving it for k equals 0. So if you try solving it for k equals 0, so try special values, e.g. try solving it for when x is 1, k equals 0, that works. And that's sort of evidence that, well, there's one or more real solutions when k equals 0, because x equals 1 is one of those. Maybe there's more. One or more real solutions when k equals 0. As a result, I think that eliminates B, C, and D. So I think Tom had done the question 10 minutes ago when Tom said that. Okay, so sometimes you can eliminate options because it's multiple choice. If you can eliminate some of the options, then it's okay to kind of go with your hunch on the remainder one to work out which one of those you want to select. Guessing can give you marks if you get the right answer, I suppose. If you put nothing, you get no marks. If you tick the wrong box, you get no marks. So nothing to lose, might as well tick a box. If you've got it down to a 50-50 by eliminating some of the options, then if you guess, that's like expectation 50% of the marks, right? 50-50. Probability question. Right, okay. Yeah, Matt I think it's bigger than or equal to 0. Oh, I need to think about 0. Because when k equals 0, I can't remember the answer to my own question. And it's 1 or more. Anyway, never mind. Right. Another Matt question, I think. Another one. Here's another question. Again, looks really horrible. Yeah, it looks like a mess, right? We've got polynomials inside brackets, inside brackets, inside brackets. And we're asked to find the highest power of x in this expression. So something we could do. I'll give you a moment there. There's a poll. Oh, shall I turn it on? I'll turn that on. Okay. There's a poll over in the Slido again. if you get to an answer, or if you can spot any shortcuts, or if you can spot a way to do this, other than multiplying everything out. Then I think, so long as you're not multiplying all of the brackets out and writing down all of the terms, I think you can save some time here. Let's try and do this one quickly. He says, it's my fault we were slow on the previous one. Everyone had got to A, and then I went off on a big tangent talking about other versions of the question. Okay, poll again. Oh, a bit of voting. Oh, speedy. Right, okay. So you could multiply out all the terms, right? We're asked for the highest power of x, and a surefire way to find that is to work out all of the coefficients and all of the powers of x, and then write down which one's biggest. It's going to take a long time though, because I think this has got about 500 terms when you do all the multiplying out and bring all the terms together. There's a shortcut though, so we don't care about coefficients. I suppose the options don't have coefficients on, so let's not bother working out coefficients as we go along. Let's ignore the coefficients and just work out which one's the highest, what the highest power of x is. Ignoring coefficients. This is a little bit like something called asymptotic analysis, but not quite. And also, nobody knows any asymptotic analysis for this exam, so it's not really relevant. It's something I'm interested in, but not a relevant way to do this question. Suggestion in chat is that when you multiply stuff out, maybe we could think about what the highest power is. When you take a term like this, come on pen, when you take a term like this one, okay, so when you multiply something out like this, I mean, if this was the whole question, what's the highest power of x here? So when you multiply this out, you could do it with the binomial expansion, I suppose, the binomial theorem if you want to. So you can binomial it. I think binomial gives you about 6 different terms, and they're all a bit horrible to work out, so I don't really want to do that. But I'd quite like to understand what happens when you do the binomial. What sort of things do you get? Some people are voting for the answers. Everyone who has voted so far has got the correct answer, so it's going very well. You can watch me do this question as well. When you do the binomial, or when you do the binomial theorem on this, I suppose it's like having 5 copies of this bracket. So it's like having, let's not write out all 5 of them. Let's write a few. It's like having 5 copies of this and multiplying them all out. If you want the highest power, then you can be greedy. You can say, well, the highest power of x comes from taking the highest power of x in each of these brackets. The way the binomial theorem works is that it's every combination of choices of terms in the brackets. So there's a term that comes out of the binomial theorem for something like what happens when you choose this term from each bracket. If you choose that twice, and if you choose the other one 3 times. There's a certain number of ways of doing that, and there's a certain outcome that you get when you do that. A squared, b cubed, or something. But that kind of idea about choosing terms from the brackets says something like, well, if I just want the biggest power of x, then the biggest term I could possibly get when I multiply out these brackets is what happens if I take the biggest power of x in every bracket that I'm offered, and I multiply those together. That's the sort of biggest term that I could get coming out of this. So here, for this little bit of the calculation, I think the highest power here is x to the 25, because I could have 3x to the 5 to the power of 5. I'm ignoring the coefficient of 3 to the 5. So I could have things that involve x to the 5s. The other terms that come out of the binomial expansion all involve things like, instead of a to the 5, something like a cubed b squared. And why would I take b squared when I could have a's instead? All the a's are higher powers of x. Okay, so you can do this. This turns out to be a powerful way to think about the question. Ket's in chat, or Kate's in chat, has got 3 thumbs up for multiplying the powers and try to get the biggest one. Great idea, let's go. So looking over here, this term with the cubed, this looks a bit like x to the 18, because when you're multiplying this out, you'll get, the first time you multiply brackets, you'll get an x to the 12 term, an x to the 6 term, and a constant. Who cares about the constant? Who cares about the x6? The biggest thing going on is that x to the 12, and then I'm going to multiply by another bracket and get up to x to the 18. This one is going to look like x to the 32, so that's way bigger. Who cares about this? Sort of elimination rounds going on in between. Over on this side, we've got x to the 28. So actually, this x to the 28 is more important than x to the 25. Goodbye. Right, okay. Now there's a kind of... each one of those is raised to a power, and then there's a final match. That was the semi-final. So x to the 32 to the 5. So I've got x to the 32 plus a bunch of other stuff, but who cares about the other stuff? X to the 32 is going to be raised to the power of 5. So I'll get a huge term like x to the 160 out of this square bracket to the 5. Over here, I'll get something that looks like x to the 28 times 6, 120, 48, 168, which is bigger. So the 168 is winning, and we can forget about all of this. X to 160, I don't care. X to 168, bigger power of x. So I've got this huge power of x, and then finally, the curly brace, the whole thing is raised to the power of 3. Because it's raised to the power of 3, I'll take the biggest power of x that I had inside, which was x to the 168, and I'll raise it to the power of 3. Like cubing that whole polynomial, the biggest contribution comes from cubing the biggest power of x. So I'm going to give it x to the 504, which is d. This is what everyone says. Oh, Cecily has taken the time to type out all of the options. Thank you very much. Yes, you pick the biggest one. We're greedy. We're going to take the biggest power. Can you use a calculator? This is this is a non-calculator test. This is probably the hardest calculation that I've... Oh, is it the hardest calculation I've seen in maths? Multiplying together 7 times 4 times 6 times 3. That's pretty much the hardest sort of calculation I've seen in maths. Multiplying small integers together, but quite a few of them. So no calculators, and only... I can just about do that calculation, I suppose. Cool, let's have a quick look at the results. Everybody's got the right answer for that one. Great stuff. I wonder if you can... you can cut corners here. People have suggested in previous workshops, people have suggested ways to cut corners on this question, which I enjoy because cutting corners, saving work, could help us out if we don't want to do the multiplication. In particular, something someone suggested was that because the last thing we're doing is cubing the whole thing, the answer we get has to be x to the power of a multiple of 3, because of that cubing. 504 is a multiple of 3. We could have seen that coming. That eliminates options A and C, I think. Gets it down to a 50-50, which you would take. Like he wants to be a millionaire. Tom says we have to be careful that the highest power terms don't cancel out. And that's true, that you can run into trouble. If this question was really evil, it could be something like 1 plus x squared minus 1 minus x squared. And then that looks like it's going to be, hey, an x squared term. And, hey, another x squared term. And I'm ignoring coefficients, so the winner is an x squared term. Hooray. But actually, this is 2x. So there's not an x squared thing at all. That's a problem because there's two different sources. There's two different sources of x squared terms, and they've cancelled out. Here, it's not a problem because there's a biggest power of x. There's only one source of where it's come from. So it's going to be just going to win. And there's nothing else to cancel with it. But yeah, in general, I might have to be careful. A bit careful, I suppose. Okay, right, good. Can you go inside first? Yeah, so you can work inside, parentheses, outside first and go backwards. Yeah, so you could start by saying, this is a power of 3, I want the biggest power of x from inside. And let's tidy this up a bit. So you could start by looking at the whole thing and saying, I want the biggest power of x. That's the biggest power of x of everything inside the curly brackets. Then you've got to think about where the highest power of x is from inside there. So I think you've got to look at the smallest scale before you can start deciding which one's biggest. Because if this was an x to the 60, then that would make a big difference. So you've got to look at the small scale before you can actually decide which thing's biggest. You can structure it working from the outside in if you want to. Okay. And is it standard practice? Matt would like to know to use different shapes of brackets. Yeah, I've seen this a few times. If you've got 2 or 3 sorts of brackets and they're quite nested and different, then different shapes of brackets. There's a popular typesetting program for writing tidy mathematics called LaTeX that has multiple sorts of brackets, so why not? Cool, right, let's do a long question. How are we doing? Good. Looking at some stats, numbers, good, cool, right. Am I live? I'm still live. Whew, we're live, anything could happen. Here's a long question. So the long questions are structured like this. They have parts with Roman numerals down the side. So I. I've chopped it up, so there's a 3 and a 4 in this one. I, and IV. Sometimes the parts of the question are separate, and sometimes they relate together. So sometimes a part of the question will say, using the previous part, do this, in which case you've got to use the previous part. And sometimes it's just a good idea to use the previous part of the question. You can get marks for your working out. You can get marks for later parts of the questions, even if you skipped previous parts of the questions, which only give you marks for any attempt at any part of the question if it's correct. You don't have to use the method that we're expecting, because you might have your own method that works, in which case, which is one of the reasons I get graduate students to mark it, get them to look at this and come up with good ways to... They're good. They're really good at spotting when people have got a new method, giving it marks. What else do I want to say? Sometimes the questions use, so that syllabus of mathematics that I mentioned, there's sort of one side of maths where, like we've seen something where we're using quadratic equations, or we're using what we know about the binomial theorem. Sometimes the questions don't really use any of that mathematics. This question's sort of more basic than that. Like, it's got the language of sequences there in part 2, but it's almost like we're not really using any of the maths on the syllabus, and that can happen. So part of your preparation for math could involve looking at some actual math questions and finding out that, oh, we sometimes just ask questions about whole numbers, and we didn't really mention whole numbers on the syllabus because you know about whole numbers anyway. Here's a question about whole numbers. Right, question about whole numbers, positive integers, x1 and y1, and we'd like to find a pair of positive integers that satisfy the equation x1 squared minus 2y squared, 1 squared, x1 squared minus 2y1 squared is equal to 1. Any suggestions? What can we do? Kieran and Cecily are in on numbers 3 and 2. Thank you. Sort of fastest finger there, and there's different amounts of delay for where you are. Tom's written out parts of the question with equal signs and commas, so slightly longer response time. Right, okay, this is true. 3 squared, take away 2 times 2 squared is equal to 1, because 9 take away 8. Yes, Rose, Catherine, Anonymous, brilliant. Hang on, Anonymous has said 17 and 12. Is that your first guess of Anonymous? 17 and 12? Does that work? So 289, that's 17 squared, minus 2 times... It's a bit of an odd suggestion, but it does work, because that's 288, so that's 1. No idea where 17 and 12 came from. Cool, not the first numbers I would have thought of. I'm over in the 3 and 2 camp. The first numbers I thought of. Well, not the first numbers, I tried 1 and 1. I did 1 squared minus 2 times 1 squared, like an idiot. And then I thought, oh, that's negative. I've made a terrible error. I need to make x1 bigger than y1. And then I tried 2 and 1, and that didn't work either. Maybe you've been on this journey too. So I tried 2 and 1, and that was 0, so I felt silly there as well. And I tried 3 and 1. Yeah, we got there. We got there, right? 3 and 2. 9 take away 8 is 1. I did not get to 17 and 12. Okay, so that's nice, first part of the question. It is worth guessing numbers for this rather than trying some complicated solution technique for solving this equation. I don't think we're expected to have a solution technique for solving this sort of equation. It looks weird and new. And we're solving it for whole numbers. I don't really know any techniques for that. And also, guessing solutions is a way of getting solutions. Right, okay. Here's the kind of meaty part of the question. It's got some algebra in. Given integers a and b, we're going to define 2 sequences. I knew they were going to be sequences because of the subscripts 1. Sequences x1, x2, x3, and y1, y2, y3. There's a sort of recursion relation thing going on here. It's a bit like an arithmetic sequence or a geometric series, except it's neither. So none of the things we know about arithmetic or geometric series sort of really help here. It says x, n plus 1, so the kind of n plus 1th term in the series is equal to, well, it depends on xn and yn. In terms of those, it's 3 times xn plus 4 times yn. And similarly, yn plus 1, the n plus 1th term of that term, is defined in terms of the previous terms xn and yn, and there are those mysterious integers a and b. We're told to find values for a and b, and the thing we want is this. Someone in chat is way ahead of me in solving for a and b. I'm going to do the maths on the screen just because I want to do the algebra, I suppose. So there's this equation that we're asked to satisfy. I could read it out, but I don't really want to. It's complicated. And hopefully when you see this doesn't look, it looks a bit unfamiliar because all the equations are a bit weird. But we're solving for a and b, and we've been given loads of facts. And what I think when I see this, I want to combine these facts together, right? Like I want to substitute. I want to take this information and plug it into the equation. They've told me a fact about xn plus 1, a fact about yn plus 1, and then another thing that involves xn plus 1 and yn plus 1. We want it to be equal to, I can already see that I'm going to eliminate xn plus 1 and yn plus 1 and get it in terms of xn and yn. And then I'll go from there, I think. And already at that point, I'm willing to switch off brain and just do algebra, right? So that's enough of an idea for me to want to sort of minus. Don't switch off your brain entirely. It's worse. I did that in the last workshop as well. It's like I'm not learning, or I have particular mistakes that I make reliably, which is very spooky. Okay, so this would be something like 9xn squared, and I haven't switched my brain off too much, so I can remember that that's xn yn, or I have switched my brain off a bit too much. Minus 2 times a squared xn squared minus 4 ab xn yn. Oh my word, this is much harder doing this on the board than I thought it would be. Okay, so I've got some terms. I think what I want to do is something like, I want this to be equal to this. I'm going to compare coefficients. Maybe I could plug in values for xn and yn. I've got this kind of this 3 and 2 idea going around, but I don't really want to multiply stuff by 9, so I'm going to try coefficients first. If coefficients doesn't work, or if it gets confusing, then I can come back to the idea of plugging numbers in. But let's compare coefficients. Okay. So what I want to do, I want to compare xn squared coefficients like this. That's going to give me 9 minus 2a squared is equal to 1. So 8 is equal to 2a squared. 4 is a squared. I want a to be positive, so I want a to be 2. Okay, and I'm going to look at 24 xn minus 4ab xn and I don't want any xn yns in this. So I want 24 minus 4ab to be 0. So I suppose ab should be 6. I already have set a to be 2, so I want b to be 3. Oh, that is positive, good news. Okay, so I've got a is 2, b is 3. Did I win? 16 minus... yeah, so there's this weird thing going on that I've only got 2 variables, a and b, but I've kind of got 3 coefficients, and I've stopped here because I've solved for a and b now. I can start engaging brain, I guess. Turn brain back on. That's a bit weird that I was about to do sort of 16 minus 2b squared and set that equal to minus 2, but I didn't get a chance to do that. If I had, I'd have spotted that, okay, that does work, because with my value of b being 3, I've got 16 minus 2 take away 2 times 9 is 18, so this is minus 2, so that does work. It's a little bit odd though. I've got 3 equations and only 2 variables, but I've got lucky and I've solved all of them. Maybe that's a clue that there's something clever going on in this question, but I just disengaged my brain for about 5 minutes, so I haven't spotted it. Right, okay, that was nice. We've worked out some values of a and b. Feeling good about this question. Let's look at part 3. Okay, so quick recap, what have we done? We found some integers that do the equation. We found some integers over here that set up these sequences so that some equation holds true. Right. Part 3 says find a pair of integers, big X, big Y, which satisfy big X squared minus 2 big Y squared is equal to 1, such that big X is big, it's bigger than big Y, and big Y is big, it's bigger than 50. Okay. So now I've got to think, because I don't know ways to solve that equation. I don't know maths about that, right? So some parts of this question involve me just do some algebra. Off we go. Try some small numbers. Whereas here I've got to really think, because I've got to find things bigger than 50. And we could start by bashing numbers in and having a go, just try it out, 2y squared is going to be even, so x squared is going to be odd, so x is going to be an odd number, so y is, I think, going to be even, so yeah, something like that. We could bash it like that, so then if y is even, then x is something to do with 8. And I don't really feel like I'm getting anywhere with that. And the reason I like this question is that it involves the previous part. I've split it onto separate slides, but I'm going to try it and go back and combine them together. Oh, excuse me. End of slideshow. So let's put a quick recap up of what we've got going on. Up here we found x1 is 3, y1 is 2. Over here we found a is 2, b is a was 2, b is 3. And brilliantly we have this equation that holds. And now in part 3 we want x squared minus same mistake again, x squared minus 2y squared is equal to 1 with x and y both really big. And there's a relationship to the previous question. This is kind of testing whether you understand what we were doing in part 2, which is the part where I disengaged my brain and just did some algebra. What was the point of that? What did we achieve by doing that? So it's possible that people are multiplying numbers together now. I think I'll take the description. I think I'd like someone to say it in chat. I think. What's going on? What's the link? How can we use part 2 to find these big numbers that do x squared minus 2y squared is equal to 1? There's no poll for this one. I'm just going to say. Just going to see if someone can give me an explanation. So part of these questions, I suppose not this one yet, but sometimes these math questions get you to explain your mathematics or explain what you're doing, explain how you know you've got the right answer, something like that. So it's good to be able to put things in writing, which people have now done. Let's have a look. You can sub in part 2. So Tom says part 2 gives us new solutions based on solutions that we know work. See if we can get that a little bit. Matt's on a calculation, 17 and 12, which is a little bit the same. I think sub in the left hand side to get larger values, and Matt's got some larger numbers. Cecily, I think it's pretty best we can find the relation between each of the terms in the sequence and find numbers x and y, working them out from our original numbers in part 1. So this equation that I kind of glazed over what it was, what it's really saying is that we've chosen a and b carefully to make sure that x squared minus 2y squared at the n plus 1 terms in the sequence, x squared minus 2y squared is equal to what x squared minus 2y squared was for the previous terms in the sequence. That's great news because it means things like x2 squared minus 2y2 squared is going to be equal to, so if I put in n equals 1 into this equation, that's going to be equal to x1 squared minus 2y1 squared. And we carefully chose x1 and y1 so that would be 1. So these things all link together to give me this chain of equalities, so that all the numbers that you generate from these sequences turn up in these pairs xn and yn, and they all have xn squared minus 2yn squared is equal to 1. These sequences give you a way to generate new solutions to that equation that we're trying to solve. That's really great news. All we have to do is actually apply these rules, xn plus 1 and yn plus 1, actually apply those rules to work out more values of xn and yn. So for example, we might work out x2 is equal to 3 times x1, again, plus or minus, plus 4 times y1 was 2, so that's 9 plus 8 is 17, and y2 is equal to a times, oh my word, I've got to really think now, a times xn plus b times yn, that's 12. So I get that 17 and 12 pair that I think someone put in chat earlier on. and you can keep going. So these numbers are big. They have 17 squared minus 2 times 12 squared is equal to 1. If you go again and use these ones, you can work out x3 and y3. The user with the username Matt Parker says that they can keep going on infinitely, to keep going to get bigger and bigger numbers. I'm going to stop here because I've got numbers that are bigger than 50, which is the thing in the question. It's kind of amazing that these work, right? 99 and 70, I wouldn't have guessed them. 99 squared is 9,801, and 70 squared is 4,900. So it does work. That is one. It's kind of surprising that it works out. So this gives you a way to generate new solutions. Yeah, Ket says sub the left hand side in, and it's equal to 1 to get larger values. Right. Okay, brilliant. So this gives us, amazingly, a solution with large numbers to x squared minus 2y squared is equal to 1. Let's look at the last part of this question. Part 4 says, using the values of a and b found in part 2, so using part 2, which was the thing where we set up this sequence of numbers so that x squared minus 2y squared would stay equal to 1. What's the approximate value of xn over yn as n increases? Okay, do you want that slide on, or do you want the previous slide? We'll leave it like that, I suppose. So this is again testing. Do you understand what we've been doing by generating these xn and yn, those sequences? What's going on? It's just asking you for a number for what that ratio is. No poll for this one, but someone in chat has said they get close to root 2. I have a reason why it gets close to root 2. This question doesn't quite ask for an explanation, but I think it would be a good idea to put some explanation in, just in case. If you put explanation in, then you can still pick up method marks, even if you make a mistake. If you've got a good method, but you make a mistake, everyone makes mistakes. If you have a good method, but make a mistake, then you can still pick up marks for your method, even though you've got a mistake. Yeah, otherwise it's a bit risky. If you just write down root 2 and don't write down anything else, then if it's not root 2, it's very hard to give you any marks. Yeah, so an anonymous person says, let 1 equal 0. But that's pretty much what I want to do. So 2 observations. As you keep generating, oh hello, as we go, let's put spaces between words. As we go, xn and yn get very large. And they still have xn squared minus 2yn squared is equal to 1, because of the thing we were saying before, that all of these chain together very nicely, they're all equal to x1 squared minus 2y1 squared, which we set to be 1. As we go, so these get very large, and this is true. So xn squared is equal to 2yn squared plus 1, but yn squared is huge. Yn squared is much bigger than 1. We already saw an example where yn squared was like nearly 5,000. They're huge. If we keep going, then we'll get to massive numbers. You know, xn squared is over 9,000, so it's just an enormous number. And in particular, who cares about this plus 1? Xn squared is roughly equal to 2yn squared. So we can then rearrange this a little bit to say xn over yn is roughly equal to the square root of 2. So it is root 2. Person in chat said that. Yeah, good, right. So it works out to be roughly root 2, which is quite nice. Maybe this gives you a way to approximate root 2. So as you generate these numbers, you get 99 over 70 is about root 2. It's a little bit good. If you generate some more, I think Matt in chat gave me some more numbers somewhere. I can't find them, but finding some more solutions along the way gives you better approximations to root 2 if you want to do that with them. It's always kind of nice that we've solved this equation exactly, and then you can play around with it to make approximations to root 2. Oh, Tom wants to know, and thumbs up from somebody else. How does this method of approximation, where have we used the fact that we're using a and b found in part 2? Good question. And the answer is kind of here. It's only because we used the right values of a and b that we had this fact at all. We want this fact. We want this so that we can say that, hey, as you generate these numbers, you still have x squared minus 2y squared is equal to 1. If you use different numbers, then x squared minus 2y squared could change and be some huge number that maybe we couldn't ignore as we went along. Oh, somebody else has replied. Don't you need to say 3ky plus 4y over 2k equal to k and solve? So you could set it up like that. So yeah, there's maybe an alternative way of doing this where you write it in terms of the previous term and then solve a thing. Yeah, you could do that. I think you could do something like that. So there's this alternative way where you write xn plus 1 over yn plus 1 in terms of the previous things. 3xn plus 4yn, 2xn plus 3yn, and then try and work with that and say maybe that's equal to, so if the ratio is about the same, then I could write that ratio as something like 3k plus 4 over 2 plus 3k or something, and then solve. Maybe I could go and do that. Oh, I've never really tried it like that before. I might try that now. We're going to wrap up in a moment because we've just gone past the end of time. The end of time? Goodness. I thought it would have looked more exciting than that. I'm not really sure where that's going. Matt's given me another approximation to root 2. Oh, it's pretty good. 577 over 408. It's a pretty good approximation to root 2. Oh, I like that. That's good. That's made it look like this is good. 577 divided by 408. Pretty good. Okay, so I hope you've enjoyed looking at math questions. Thank you for joining in with the multiple choice and putting your great suggestions in chat. If you like this sort of thing, then we're running at the moment. Oxford Online Maths Club is a lot like this, with different problems and kind of mini lectures and just showing you bits and pieces of maths with chat open for brilliant people like you to join in. That's every Thursday, and there's about a million links to it on different open day things, so I won't mention it anymore now. From the 5th of August, we're going to run a Matt live stream, which is going to be exactly like this. That's going to be a different sort of live stream where we just do Matt problems. We ran it last year, so if you want to sneakily look at last year's Matt live stream, let's see if you can find the Matt live stream from 2020. If you want to look at other bits of maths. Otherwise, I'm going to say goodbye, and I will see you if you're joining us again for more Q&A and talk to tutors and things like that. And I've got some next steps to kind of wrap up, like how we started the day. If you're joining for that again, that'll be at 4 o'clock. So see you in half an hour. Otherwise, I hope you've enjoyed the open day. I hope you enjoyed the Matt workshops, and I will see you around. Good. Someone said Matt likes the Matt questions. There you go. You've been waiting. That's why you put Matt in the box, isn't it? Matt liked the Matt questions. I love it. And someone from last year's Matt live streams has joined us in the open day stream here as well. Good stuff. Right. Okay. See you back in the other live stream button for 4 PM for Q&A and other chat, or just around on one of our other Oxford Live Maths things. Oh, Catherine's put another approximation to root 2 in chat. Okay, right. Cool. I'm going to stop being live. Take care, everyone. Have a nice afternoon. See you in half an hour, perhaps. That one.